Afternoon, everybody. I'm going to start this presentation with a familiar story, the story of Sisyphus, who was condemned to roll a boulder up the hill, and every time he reached near the top, the boulder would roll back down. This is emblematic of the problem that we have in OT cybersecurity, in maintaining and managing our OT system cybersecurity, where every time if we get to patch one of our systems, another vulnerability is found, another patch is released, taking us back to square one. We need to break away from this cycle of responding reactively to threats and reach a more stable and proactive position in cybersecurity. So today I'm going to talk about a technology that's promising to take us to this stable position. But let's talk numbers first. In the UK, between 2021 and 2025, we are set to spend close to $12 billion on maintaining and achieving an acceptable level of cybersecurity in our regulated gas and electricity market. Majority, or a good portion of this fund, is going to be channeled into maintenance and upkeep of the cybersecurity controls, of which patching and updating our systems is a good proportion. In a study by Microsoft and Google independently, they have confirmed that about 70% of all the existing vulnerabilities in our software state are attributed to memory-related vulnerabilities. So putting the two together, you can see how billions is going to be spent in managing the cybersecurity that are related to memory-related vulnerabilities. This problem is compounded even further in industries like utilities, where you have distributed assets, and the geographical distribution causes additional challenges in maintaining cybersecurity. Memory management is not a new problem in the OT. It's a legacy issue risen by lack of attention at the foremost to increasing the ability of memory management in OT devices. Whilst in traditional IT, we've come a very, very long way in maintaining the agility of memory management. This has been neglected in OT. So I want to just get a little bit closer to a specific industry. In the gas distribution, we rely heavily on measurement of gas quality. So in the UK, last year, about 60 billion cubic meter of gas was transported in our pipeline. That equates to roughly $55 billion. This was calculated based on the calorific value of the gas that's transported. That's calculated and relies heavily on the gas quality measuring systems. The gas quality systems are, in very simplistic terms, a gas analyzer, a chromatograph of some sort, and a supervisory system that does the calculation. Inherently, they are very much dependent on our favorite protocols, Modbus, to talk to each other. And effectively, the $55 billion of gas that was transported in our system was effectively dependent on the correct functioning and accuracy of the system. And so today, we want to have a little bit deeper look at this in our deep dive and use this as an example to look at some of the leading technologies. We've taken a Modbus server and Modbus client system that we've seen a lot in the industry. You don't need to read the code. Is to show how very little code takes to stand up a Modbus client and server system. This particular one is actually being used in the gas industry quite heavily. And in it, there is a number of, Modbus itself is inherently insecure by the virtue of having a number of limitations in buffers, etc. But in this particular implementation, there are a number of vulnerabilities. One of them is the lack of input validation, and if you see on, so there is a variable IR SRV, which is not, doesn't have any input validation, and so it is easy to go outside the bound that the server is operating on and cause all different problems. So if we have this server starting up on having a number of input registers serving and waiting for a request from a Modbus client, what we expect is that if we request, say, 2 input registers from this server, that we get a healthy response, which would look something like this. This is a healthy response that we expect from a normal Modbus server. Now, what happens if we go beyond these 10 input registers where there is no validation on the server? We would end up crashing the server. And this is because we end up writing in additional memory cells that are not meant to be written to, causing corruption. You can see how you could start injecting memory vulnerabilities and injecting code or reading variables that you're not meant to be reading, right? So how do we resolve this problem? This isn't an issue that is related to Modbus only. This problem exists everywhere in the OT. From protocols to drivers and runtimes. A recent notable one that came out in 2021 was the bad alloc. Don't know if any of you have seen it. That affected a very, very wide range of OT systems, from controllers to EST systems to relays, even the Mars Perseverance rover, which is a lot harder to patch now. To ASIMO and our military aircrafts. This highlights a very, very serious problem that our, not only OT, but our digital economy that supports billions of people all over the earth is hinging and is dependent on the correct functioning of memory access architectures, of which there are only a handful of. This exacerbates this problem when you think about it, because we're no longer looking at just the OT, and this is endemic everywhere. And so there was a series of funds that was put together in the UK, about £100 million in 2019, to look at creating a new technology, a new memory access architecture that would try to resolve or remove a lot of these inherent vulnerabilities in the way we manage memory. This 100 million was backed by another $270 million from the industry, from the giants like Google and Microsoft, to smaller innovators like us, to have a look at how to create a technology and how to deliver that to the industry, and what are the use cases around it. At the core of it is the ARM chip. So this program is fundamentally supported by ARM, the chip manufacturer, and Cambridge University through years of innovation and research. The ARM chip implements CHERI. CHERI is Capability Hardware Enhanced RISC Instructions, which is, so CHERI has been in the industry for decades, but the implementation of it at the hardware level on the system on chip is novel. Its approach is, if you take older or current memory access architectures where having the address in a memory is almost like having the key to a building. As soon as you're inside it, you can access with very little restrictions the memory cells and the information within them. Morello looks to turn this completely on its head, where by introduction of a new data type called capability, it looks to add token of authority to each of the requests within a program, where if you are inside the building, you can no longer access every room in the building, and you need to have almost a digital card to be able to access each room based on the access that you are given in that software. And this is, so if you look at memory addresses in classic architectures like x64, where 64 bits memory addresses point to like a door number at a building, point to that address where the information is stored. In Morello, or in CHERI implemented on Morello, this turns into a fat pointer where your addresses are still there, but you are then adding permissions, you're adding additional capabilities that are continuously monitored and assessed throughout the runtime in a software. And this is all done on chip rather than classically carried out on the software during runtime. This allows very fine-grained memory protection, so that now that you are inside the building with your access card, having access to a particular room, you still need permissions to access the coffee machine or the microwave. So during the program execution, the timing, the access to read and write to every memory cell is controlled and monitored continuously, again, by the chip itself. This allows a lot of agility during execution, so very little overhead in terms of software execution, and it provides a lot of compartmentalization at a software level. Again, take a ship as an example where you have watertight compartments. The breach into one compartment doesn't sink the ship. It's very much the same where this control is carried out at a very, very fine-grained level on the chip. Morello brings a clear step change and innovation, and with it comes the claim of reducing software vulnerabilities, because that 70% vulnerabilities should go away. So we wanted to understand how does that apply to us in the OT. And so as part of the Digital Security by Design initiative by the UK government, a project was defined, the DefGrid project, run by a partnership between Deltaflare, that's us, and SGN and the University of Strathclyde. Deltaflare is the technology partner, where we look to port our Phoenix software, which is currently securing the gas industry in the UK, from x64 architecture to the Morello architecture. SGN is the second largest gas distributor in the UK that supports us by giving us access to their networks. and their programs, and the University of Strathclyde provides us with additional research capability. So as part of this project, we were given the task of looking at the additional security benefits that Morello provides through the implementation of Phoenix security platform into the utilities. DefGrid is the only demonstrator that looks at implementing the Morello within the CNI, within the critical national infrastructure. There are a number of other demonstrators that looks to test the capabilities of Morello within other industries like banking and telecommunication. This is a 3-year program of which we've completed 2 years of, and we've demonstrated already a lot of capabilities and a lot of value add to the industry using this technology. So taking what we've seen so far on the vulnerability that I demonstrated early on the Modbus system, the question is, how do we take Morello, how do we apply our legacy software base onto Morello? Is that possible? How much effort is required, and what are the benefits and value adds to it? Before we get into running software on Morello, the new architecture comes with a number of software ecosystem. So this has been supported by Cambridge University and all the other organizations like us and the University of Strathclyde, where we've worked to port a number of other supporting software around Morello to create this ecosystem for use by the others. Running software before even running it on the Morello, just compiling it using the Morello compiler flags up a lot of the memory vulnerabilities. So without even running and gaining the benefits that are required at runtime, you immediately get a lot of free added values. But to really be able to get access to the capabilities that the Morello provides, you need to modify your software a little bit. So the software needs to include header files that provides the API access to talk to the hardware, to be able to interrogate and provide and glean the benefits from the hardware. It needs to be compiled with the right compiler. There are a number of, whether you want to cross-compile or compile on the hardware itself. That would be the first step. So if we were to do this and run our software again, it would still crash, but this time it wouldn't crash because you've written on cells that you shouldn't have written to. It would crash because Morello would have captured that vulnerability, but not so gracefully. So the next step would be for us to understand why there was a crash. So signal header, which is a standard header file in the C libraries, has been modified to include now hardware exceptions that Morello spits out and provides to us. So there's a suite of them which we can grab and now get very, very detailed information about what's happened with the memory, what are the vulnerabilities, or rather what are the exploits that have been trying to be put through to the hardware. So at this level now we are getting a lot more contextual information. The next one is to make sure that when this vulnerability is exploited, that we capture it, we discard it, and then we still maintain the operation of our asset, which is key in the OT. So to do this, we place markers inside the software to take us back to a known and acceptable part in the code, and with this, we're able to then grab something that was going wrong, that was unexpected, discard that, and resume our operation. So that's, in very simple sense, that's the gist of it. So if we were to go back to our original example, where we had a client requesting 1,000 input registers from a server that wasn't ready to receive that request. Previously, when that happened, at this stage, our server crashed, which would have been a denial of service in the OT. But this time, we're able to grab that, stop this request going through. So you can see that Morello has now identified that there was a capability bound fault. We can then map that to Modbus errors and provide even more contextual information. This is all done so that this particular exception was risen from the hardware provided to the operating system, which we can now make decisions on. And when that happens, we can discard that bad request and resume our service. This is truly revolutionary. So without having to go back and rewrite our code that are vulnerable, we're able to, with a slight modification, using this hardware, run the same code and now discard hopefully 70% of our vulnerabilities. Right, so we've established that we needed a step change. We needed to break away from the way that we've been operating our assets, whether it's in the OT or otherwise, when it comes to memory vulnerabilities. In the example on the right, where it's an excellent example of how a paper that was written on a standard machine controller was taken up by back then General Motors, that created a demand on the industry. So they took this paper, they then commissioned what turned out to be the first POC, later on Modicon, and around it started the industry, started a new standard, 61131, that created what we have now as modern industrial control systems. Where we are now with Morello program, the DSPD, Digital Security by Design program, and the DefGrid initiatives are that catalyst. We have demonstrated that this technology exists. We've demonstrated the art of the possible. And now it is for the industry, for you, to create that demand, for the equipment manufacturers to take on this proven technology and to see what we can do with it and to create this change and basically drive the new memory secure, memory safe OT. Thank you very much.
We have one question.
There's a question?
So if that's okay. Yeah,
okay.
Just here.
So is this memory protection for the OS application, like all of memory?
All the memory that's available to the program, is that what you're saying?
Yeah. The firmware OS, or just or is it all combined?
No, everything, yeah. So from anything that's on the hardware, so from the hardware up, the operating system is also monitored with the same way. And that's the key difference with this implementation, that all the memory access are challenged at the hardware level. And so anything that's running on the metal is effectively protected by this technology.
So when an application runs, it has like a token associated with is it in the code, the process? How does it know?
So what you do is you define your capability or the requirement that you have for read-write access to whatever granularity that you like. If you are writing code from scratch, you can do this for all the variables if you like, or you can then, based on, the hardware, when you start up, it knows where the memories are, and if you're trying to go outside of that, based on every instruction that comes in, it can then make the right decision. So if you are taking legacy code, you probably don't want to go through and rewrite and add a lot of capability to it. So you can run it with less, like I just demonstrated. But if you're writing code from scratch, then you have a lot more ability to be more granular if you wanted to.
I see. So you're telling the OS, this is the range of this memory for this function.
That's right. Yeah.
Okay. Thank you.
And if anybody wants to get their hand on one of these hardware, by the way, either come see myself or my co-founder, Thomas, and I'm sure we can find a way to hook you guys up.
Much more.
Thank you.